welcome to the second lecture accompanying Chapter 2. All right, so in this lecture, we're going to talk about the moon and a little bit about the planets. And the perspective is going to continue to be how we see them from the surface of Earth, because that has been the common thread through everything that we talk about in this chapter. Everything in video 1, everything is video. They are surface-based, Earth-based observations. Okay? So, let's get into the moon, including the phases that we observe from the surface of Earth, and eclipses, both solar and lunar eclipses. Okay? All right, so first of all, let's lay down some basics, some numbers, okay? So here we have a 2-scale photo showing the Earth and the moon. Okay? So here we have the moon up here. There's that small black dot, and here the Earth, a slightly larger blue dot. The scale here is showing their relative diameters and their orbits, all to scale in a single picture, which is kind of rare in astronomy because the distances tend to be so much greater than the actual size of the celestial bodies. But in this case, the moon is actually fairly large compared to Earth, and it's fairly close. It is 60 Earth radii away from us. Okay? So the moon is 60 times further away from us than we are from the center of the Earth. Okay? We can see that the circle or the orbit of the moon is not a perfect circle. It is an ellipse, and at its closest approach, it's 356,000 kilometers, and at its furthest distance, it's 407,000. Okay? And then we can see here, this much thicker blue line is the orbit of Earth relative to the moon. Okay? And it points out that the sun is 15 meters away on that scale, which is like 45 feet, right? So if you took this like page, and then you imagined, and this was the printed page originally, depending on how large you see in your screen, but you imagine the original printed textbook, or if you have the printed textbook in front of you, and then you have to go 45 feet to get to the sun, so a much greater distance. Okay? Furthermore, we have that the full phase of the moon is 27.3 days. Okay? Or I should say the lunar phases are a consequence of the orbit, which has a period of 27.3 days. That is the period. That's just the time to make a full orbit around Earth. Okay? Other facts about the moon we'll get to. There's an important one, and that's another tilt question. Not so much the tilt of the moon itself, but the tilt of the moon's orbit. Okay? But we'll get to that. Okay? So why do we see phases of the moon? Okay? So here we have a photo where we imagine someone holding a ball, and then that ball kind of being held at different orientations around them. And there's some light over here, right? Some bright light. So if you were to perform such an experiment, and you held the moon between yourself and the bright light, then you're only going to see this shadowed side of the moon right here. Okay? Because the illuminated side of the moon is going to be invisible to you, right? Your eyes can't see this bright side of the moon because your head represents what? Earth, of course. All right? But if you were to continue to rotate your arm, okay, but keep the light in a fixed location, okay, so keep the light here, then as you orient your arm differently relative to your head, and then you looked at the ball that you're holding, you would see that now some of it becomes visible. For example, we would get to a point here after 1/4 rotation, and by the way, we're going in the counterclockwise direction, right? So imagine the arm getting rotated this way, all right? And you can see the arrows as well, being consistent with that. You get to the point, you'd look at the ball, and you'd see half of it bright and half of it dark, okay? So because half of it is picking up the reflected light from the sun, this dark half, you'd be able to see, but it would be dark, all right? It'd be shadowed, okay? And then as you continued around, once the moon was on the far side of the light relative to your head, okay, then you would see a full moon. It's fully illuminated. Now notice that this picture is drawn in such a way that the moon is kind of down below the shoulders of the person holding the ball. And that's actually very useful to think about, because maybe we don't want to think about the fact that the light is hitting your head and then your head is creating a shadow. So once you put the ball behind your head, you'd be like, oh, wouldn't the ball just be in the shadow of your own head? So you wouldn't see a full moon? The issue is resolved by the fact that we just consider the ball as not exactly lined up with your head, so the light's still getting to it. We'll come back to that idea, okay? And then we can continue round, eventually get to a point where we have half illuminated and half darkened again. That's a third quarter moon. And then finally the cycle restarts. Now let's pay more attention to the names, okay? So when all you could see was the shadowed side of the moon, that was a new moon, okay? A new moon is an invisible moon, hence the picture doesn't show a moon at all, the picture in the box, okay? In real life, you can kind of see the outline of it because there's still light that's reflecting through kind of the dust, not really atmosphere, but the dusty surface of the moon. So you can see an outline of the moon on a new moon, okay? But only if you catch it at just the right time of the day, okay? Furthermore, we have a waxing crescent. That's once a moon starts to become visible. Then we have a first quarter waxing gibbous, finally a full moon. That's halfway through the whole phase. Then we have the waning gibbous, because now the moon is starting to shrink. Waning means shrinking. Waxing, by the way, meant growing. Okay, and gibbous is just the term that's anything between a quarter and a full. All right. Then we get to a third quarter. The cycle is about to reset. Finally, a waning crescent, and then back to a new moon. Then it starts all over again. Okay. One weird thing about the terminology is the idea of a quarter. Now you think about a quarter. Well, a quarter makes sense as far as that you only see a quarter of the moon. Because consider that we have this section. This is the ball orientation that corresponds to a first quarter. Well, this person holding the ball can't see the side of the ball that's far from them, which was the same reason they couldn't see the illuminated side with the new moon. Thus, they couldn't see any moon at all. So in a sense, the only surface features that they're seeing represent 1/4 of the total surface of the sphere that is the moon. Hence the name, quarter moon. Although full moon is a little misleading because, again, we're actually only seeing half of the surface. There's a whole side of the moon that we're not seeing. Okay, and we'll talk more about that side of the moon we're not seeing in a minute when we talk about an interesting aspect of the moon's orbit. So full moon's a bit deceiving. We could really call it a half moon because you're seeing half the surface. But of course the term is full moon. Now the last thing I'm going to talk about is the timing here. Because let's think, just being oriented between you and the sun, and that's you being the earth, of course, corresponds to a new moon. But what does that mean? Because, of course, the moon isn't a fixed object. It's an object orbiting Earth. And, of course, unlike the head of this observer, the Earth is not a fixed object. It's an object that's rotating about its own axis, thus giving the perception of everything rising and setting, including stars, like we talked about in the previous video. So what does that mean then about the rising and the setting of the moon? Well, the head here is spinning, if we imagine it being more like the Earth, and it's spinning much faster than the moon is orbiting. Okay? Because again, the moon takes, for this whole process, the moon takes 27 days, just over 27 days. Okay? Well, in a single day, the Earth spins all the way around its own axis. So the moon doesn't move much between phases in a single night. It would be only 1/27th of its phase. That is noticeable sometimes if you're making very precise measurements. So unlike most things, as the moon rises and sets, it does undergo a little bit of change over a single night, but it's tiny. Okay? So we can effectively think of the phase of the moon not changing over a given night. But it's definitely rising and setting as perceived by us because we're spinning, right? With a period of spin of 24 hours. Okay? So then the point is that when the moon is between us and the sun, it must rise and set exactly with the sun. So that means that a new moon rises and sets with the sun. It rises in the morning and it sets at sunset. Okay? Whereas a waxing crescent rises a little bit later. Now it's lagging behind the sun. It rises mid-morning, maybe 9 a.m. if the sun rose at 6. And then it sets in the late evening. Okay? Does that make sense? So it sets after, because it's lagging now. So let's say the sun sets at 6, it's going to set at 9. Okay, so it sets after the sun, late evening. Okay? When we get to the quarter moon rises at noon because now it's lagging a full kind of like half cycle behind, well, really more a quarter cycle in fact. So it's lagging a quarter cycle behind the sun. So it rises at noon and sets at midnight. All right, that's a quarter moon. And that's why you see quarter moons in the sky a lot during the day. I'm sure you've noticed them up in the sky. You're like, oh, there's a moon in the sky, and it's like a quarter moon, right? And it's during the day. Okay, it's very beautiful, in fact. The full moon, on the other hand, because it's completely out of phase, out of cycle with the sun, rises at sunset. Once the sun's gone, then it starts to rise, and it sets at sunrise. Okay, there's no way around that. You can't have a full moon any other time, because if it was rising and setting of the sun, how would it get light to reflect? So the two ideas go together. And then finally, the third quarter, the jump ahead, rises at midnight and sets at noon. So it's just the exact opposite of the first quarter. Now, that actually makes a fun little thing, because if you see a quarter moon during the day and you see it in the western sky, then you know that, well, it must be a first quarter. Because first quarters are, I misspoke there. It must be a third quarter. Because if it's in the western sky and is visible during the day, that means it's on its way to setting at noon. Because, of course, it sets in the west. So a quarter moon in the western sky is a third quarter moon. Because by the time the sun rises, basically the moon is at its highest point in the sky. And as the day goes on, it continues to set. Okay? And then it's setting at noon. On the other hand, if you see a quarter moon in the eastern sky, all right, well, that's going to be also in the afternoon, but probably more noticeable where you see it in the sky, then that has to be a first quarter moon. So you know just by where you see the quarter moons in the sky what phase you're in, which tells you that are you approaching a full moon or are you approaching a new moon. So you can quickly, without even looking it up, figure out what phase, what part of the cycle you're in. All right, so a lot of information there to process, a lot of things to think about. Okay? All right. So half of the moon is illuminated by the sun, and half is dark at any given point. We can sometimes see that illuminated half, sometimes we can't. Sometimes we can see some of the illuminated half. Okay, all right? So let's continue on, because there's more details to reveal here. Okay? So it's just summing it up. These are all the phases that correspond to waxing. New, crescent, first quarter, gibbous, full, and all the phases that correspond to waning, shrinking. All right? So gibbous, last quarter, crescent, and then back to new. Okay? Points out the time where you'd see it, as I was talking about, and then just the terminology, getting less full and getting fuller for waning and waxing, respectively. Okay? So notice this. The full cycle takes 29.5 days, whereas the orbit only took 27.3 days. Why is that? That's because to get the full cycle, you have to take into account the fact that the Earth is moving as well as the moon orbiting. Once you take those two things into account, you end up with a longer phase for the full cycle than for the orbit. Okay? All right. So, thought question. It's 9 a.m. And I will always have versions of these on the exam. These, like, you see a moon and you have to figure out what phase it's in and so on, okay? So there's so many different versions of these. It's 9 a.m. You look up in the sky and see a moon with half its face bright and half dark. What phase is it? Okay? Now, you might not be able to answer this yet, but this is the type of question you need to be able to answer confidently and be able to visualize it and figure it out. Okay, so think about it. Third quarter. All right? Third quarter moon. Okay? 9 a.m., you see it. Okay? Make sense? Okay. Now the thing where what I was speaking before had to be, I was trying to say the shadowed side of the moon, because there's a term we use all the time called the dark side of the moon. Okay? And the dark side of the moon, when we use that term, refers to the side of the moon that we never see from Earth. Well, what does that mean, the side we never see? Well, it all has to do with this idea of a synchronous rotation. The moon rotates exactly once with each orbit. Okay? Because at this point, we've only talked about the moon's orbit and talked about how that orbit interacts with the sunlight. Okay? That's all we talked about so far. We haven't talked about the moon's rotation. Well, it turns out that it is rotating. But unlike Earth, which makes a full rotation every 24 hours, the moon makes a full rotation every 27.5 days. Okay? So orbit, period, equals spin period. And by spin period, I mean rotation about its own axis. And you can imagine doing that, right? Like, look at this person here, acting like the moon. They spin at a really slow rate as they walk around this central pillar. And in doing so, they ensure that only their front side faces the pillar. If they spun a little bit faster, then they'd end up sometimes showing and eventually showing their backside to the pillar. If they spun a little bit slower, then they would end up showing their backside of the pillar. But if they spin at exactly the rate that it takes for them to make a full circle, then they'll never show anything but their front side to the pillar. And that's what the moon does. So that means that the backside of the moon is never visible to us unless we go into space and fly around the moon. You cannot see it from Earth. Even something that, like an Earth-based satellite, wouldn't be able to see it. Okay? You have to actually get on the far side of the moon. You have to physically fly those 150,000 kilometers to look at the far side of the moon. Okay? Quite a feat. Now, where does that come from? Why? This just seems like an unbelievable coincidence that the moon has a synchronous rotation. Okay? Well, it turns out that it happens naturally from the effects of the tides on Earth and the way that takes energy away from the angular momentum, from the motion of the moon. Okay? It's called tidal locking. And we see it elsewhere. Okay? There are other examples. Mercury is so close to the sun that it's nearly tidally locked with Mercury. Over billions of years, the same thing has happened. It is slowed down in its axial rotation, so its orbit and axial rotation are very close to each other. So it almost always has one side that faces the sun. You can imagine how baking hot that one side is. Okay? Now, it's not quite that way, so eventually it does have all of its sides face the sun, because if it's slightly out of sync, that's all it takes. It has to be perfectly in sync. All right? Now, if that's the case, if the moon has lost energy to cause this synchronization, then will the moon continue to lose energy? Yes. Does that mean the moon will slow down in its orbit? No. But it doesn't mean that its orbit will get bigger and bigger and bigger. So the moon is moving further and further away from us, a few centimeters every year. Okay? A few meters, I think. Okay. So with that out of the way, with synchronous orbit, phases of the moon out of the way, definitely something you want to study, let's get on to the other big thing about the moon. And that's the idea of eclipses. All right? So the Earth and the moon cast shadows. When either passes through the other's shadow, we have an eclipse. Okay? So when either. So that means there are two types of eclipses. When the moon passes through the sun's shadow, and when, see, that's not well said. Let me rephrase that. When Earth passes through the moon's shadow, and when the moon passes through Earth's shadow. Okay? There's no sun shadow. Sun is the light. Okay? So we can have the moon passing through our shadow, or we can pass through the moon's shadow. All right? Those are the two types of eclipses. So let's look at this idea. Here is an eclipse caused by the shadow of the moon. And there's two terms that we're going to keep coming back to, and those are penumbra and umbra. A penumbra is the outer shadow, and the umbra is the inner shadow. A umbra is a total shadow, so no light gets through at all, and a penumbra is a partial shadow. So it's darker, but not completely dark. Okay? Partial. So that's the difference. Partial shadow, total shadow. And this isn't unique to planets. If you shine a light on something, like if you hold a ball in front of a lamp and you look, you can see the dark central shadow and the wider blurry partial shadow. Okay? So let's summarize the probably less dramatic type of eclipses, lunar eclipses. Lunar eclipses are the type of eclipse that's created by Earth's shadow. You might be like, wait, that's a weird name then. Why is it called a lunar eclipse if it's created by Earth? Shouldn't it be called an Earth eclipse? Well, yes and no. A lunar eclipse is called that because the effect, the visible effect, is on the lunar surface. So a lunar eclipse, the focus is on the moon, hence the name. Okay? And there's three types. There's a total lunar eclipse, a partial lunar eclipse, and a penumbral lunar eclipse. Okay? What are the differences? So a total lunar eclipse is when the moon passes through Earth's umbra. Okay? In that case, it is completely blocked off from the direct sunlight from the sun. The only light that's making it to the surface of the moon in that case, thus the only light that's reflecting off the surface of the moon that we can see, is the light created by our own sunsets. Because there's a ring of sunsets around the edge of the planet that are sourcing their own light. That light, much weaker, is entirely red because it's a long wavelength light, and that light then is making its way to the moon, reflecting off the surface, and thus total lunar eclipses are always red. They're beautiful, okay? Total lunar eclipses are visible to half the Earth. Everyone that's on the shadowed side of the Earth will be able to see it. Okay? I mentioned the idea because when we come back to solar eclipses, or I mentioned solar eclipses in the next slide, you'll see that solar eclipses are seen by a much smaller subsection of the population. Okay? So half the Earth will be able to see a total lunar eclipse. Okay? All right. So moving on, partial lunar eclipse is where the moon passes through part of the umbra and part of the penumbra. In that case, because the light of the penumbra is so much brighter than the faint sunset light that makes for the red moon during the total lunar eclipse, the redness is basically lost, and instead we just get a half moon. Okay? So partial lunar eclipses are interesting. They're not red, but they're neat because we get these crescent moons on a night that should have been a full moon. And furthermore, the shadow that gets cast onto the moon during a partial lunar eclipse always actually shows the Earth's curvature, thus disproving the proposals of flat earthers that the Earth is flat. Right there during a partial lunar eclipse, you can see that it's a circular source or a spherical source that's creating the shadow. Thus, the Earth must be spherical. It's just such a simple demonstration of it. And then finally, the least dramatic of all the lunar eclipses, a penumbral lunar eclipse, is where the moon passes through the penumbra, which really means it's just slightly fainter than usual. It's a paler full moon. And what do all of these have in common? They're all full moons. Why is that? Why is there that rule? Well, of course there's that rule. Because you can never have the moon in the Earth's shadow unless it's on the other side of the Earth relative to the sun. And that was this whole definition of a full moon, wasn't it? When we introduced the phases, full moons only happen when the moon is on the far side of the Earth, represented here by someone's head, relative to the sun. Okay? So all lunar eclipses are full moons. Okay? So the only time you could ever get an eclipse is once every lunar cycle, once every 29.5 days. Does that mean we always get a lunar eclipse every 29.5 days? And for that matter, why is it that the moon is in different orientations? Why is it sometimes low in the umbra? Why is it higher halfway in the umbra? And why is it even higher still all the way up in the penumbra? And then people don't always talk about lunar eclipses, so that means sometimes it must be even higher, right? Why is that? Okay, we'll come back to that idea. Okay, so lunar eclipses can occur at full moons, okay, only, as I said, and the three types: penumbral, partial, and total. All right, so now let's talk about the other type of eclipse, and then we'll talk about why we don't see eclipses every month. So solar eclipses, these are the dramatic type, and there's three types of these as well, okay, for different reasons. It just ends up also being three types. Okay, so solar eclipses can only occur at new moons. By the same logic that dictated that lunar eclipses can only occur at full moons, solar eclipses can only occur at new moons. Because the only way that the Earth can be in the shadow of the moon is if the moon is between us and the sun, which is only possible at new moons. Okay? All right, so let's look at the cases. So here are the three types of solar eclipses. First, a total solar eclipse. A total solar eclipse happens for any person that's right on that red dot. Okay? And that red dot represents the path of totality, and it is where the umbra of the moon reaches the surface of the earth. Okay? So the path of eclipse, exactly on that path, exactly where this darker cone comes down and makes a small point on the surface of the earth, is a total solar eclipse. But here's the thing. That point is quite small, because the nature of umbras is they get smaller and smaller as you get further and further away from the source that's creating the shadow. Okay? If the moon was further away, the umbra wouldn't actually make it to the surface of Earth if it was just a few thousand kilometers further away. But it does make it, just barely make it, and we get a shadow that's this size. And this is about 100 kilometers across. This is the actual shadow of the moon being cast onto the moon by the sun. Okay? Okay? By the sun light getting obstructed by the moon, really. So both, right? It's the sunlight getting obstructed by the moon, creating a shadow. Everything outside of this path of totality is partial, because we can see there's a much larger region, still not huge, but a much larger region that is the partial solar eclipse region. A couple of years ago in Northern California, here in the Bay Area, it was possible to see a partial solar eclipse. The sun got blocked off partially, and the sun looked like a crescent for a while if you had the right glasses to be able to look directly at it. Okay? That was really cool. But if you went up to Oregon, here on the West Coast, you could be in the path of totality. All right? And this shadow is moving with the moon. All right? So as the moon moves, the shadow moves. And the moon has a orbital velocity of about 1,000 meters per second, 1 kilometer per second. So that shadow is racing across the Earth at 1 kilometer per second. So then if you stand in the path of totality, it usually takes about 100 seconds. You only have like a couple minutes to be in that path of totality. Okay? It can be longer because the shadow can get stretched out depending on how it's getting projected onto the curved surface of Earth. But you're anywhere between 2 and 5 minutes. Okay? So if you're in the penumbra, you get the partial solar eclipse. Okay? So total if you're in the umbra, partial in the penumbra. So umbra, penumbra. Right? Same terms we use for the lunar eclipse because it's the same idea. All right? Much fewer people see either type. You have to be in the right place of the world at the right time. Okay? Then there's one even rarer type of solar eclipse, and that occurs when the moon is furthest away from Earth. Because remember, there's variation. There was its closest approach and its furthest approach. Well, when the moon is at its furthest distance from Earth, well, it turns out that sure enough, the umbra doesn't quite make it. The umbra instead finishes off somewhere in the upper atmosphere. Thus, no one is in the path of totality because there is no dark spot that's 100 kilometers wide being cast onto the surface of Earth. Instead, the dark spot finishes in a single point, again, some 100 or 50 kilometers above the surface. And instead, those that are in the path, so to speak, see an annular solar eclipse. Because in that case, some of the sunlight is still getting through. Another way to think about this is think about the angular size. We talked a lot about angular size. I mentioned how the angular size of the moon is half a degree, 60 arc minutes of angular size. The sun is the same angular size, okay? But not exactly. Because although the sun's angular size doesn't change that much because the distances are so great, the moon's angular size does change. It changes from 0.45 degrees to 0.59 or something, right? So there is a significant variation in its angular size. Thus, when the moon is furthest away and it happens to coincide with an eclipse, and again, I'll get to the conditions of an eclipse, which I've been hinting at, then the angular size of the moon is now not equal to the angular size of the sun. The sun is bigger, and it's just that. The moon can't quite block out the sunlight, and we get a ring of fire, which is sometimes called. So In some ways, it's not as dramatic as the total solar eclipse, because the total solar eclipse, once it gets blocked, the stars suddenly become visible. It feels like nighttime all of a sudden. The temperature starts to quickly drop. It's just really unbelievable, right? It seems so otherworldly. The annular solar eclipse would also seem that way, but it wouldn't be dark. It would just be like, oh, the sun looks like a ring in the sky, but there should be quite a bit of light coming through. Okay? All right, so all of them, beautiful, mind-boggling, spiritual events for ancient people, spiritual events for people alive today, right? Solar eclipses. Okay? Now, if all it takes is a new moon to get a solar eclipse, and likewise a full moon to get a lunar eclipse, why don't they happen every month? Well, let's discuss. Okay? Why don't we have an eclipse at every new and full moon? Okay? Well, it's because the moon's orbit is tilted 5 degrees to the ecliptic plane. Okay? Remember, the ecliptic plane is essentially the plane that Earth's orbit makes around the sun, and it turns out basically all the planets are essentially in that plane. They can be 1 or 2 degrees off, and none of them are as much as 5 degrees off. The much bigger tilt was the Earth's axis. It's a whole 24.5 degrees off from the ecliptic plane. But the moon's orbit is actually significantly off at 5 degrees. So you can see in this picture, we've drawn the ecliptic plane, again, that's just the plane represented by the Earth's orbit around the sun, as a flat surface of water. And then visualized the Earth's orbit as a tilted disk that goes down into that water and up out of that water. And thus we can see, based on this splash graphic, right? This idea that the moon is splashing down into the water when it goes beneath the ecliptic, right? This is it splashing into the water to go to beneath the ecliptic. And here it is rising up out of the water to go above the ecliptic. We see that the only times that either type of eclipse, lunar or solar, can occur is when one of these splashing events or rising up out of the ecliptic plane events coincides with a new moon or a full moon. Okay? So that means that you need this. You need a full moon near a node to get a lunar eclipse. You need the tilt to coincide with a node, because a node is called the point where the moon passes through the ecliptic. Because sometimes you can have no eclipse at all. Look what happened here. Look at this full phase of the moon. No eclipse, no eclipse. Because the moon right here passed up out of the ecliptic plane when it was in a, let's think about it, this would be a first quarter. And then it passed back down below the ecliptic plane right here at a third quarter. But neither first quarter nor third quarter can lead to any type of eclipse. So that means the nodes, because a node again just refers to when it passes through the ecliptic plane, the nodes didn't coincide with the correct phases of the moon. Thus, no eclipse. Okay? On the other hand, this example over here would lead to eclipses, and so would this. Okay? This one here, a new moon near a node, would lead to a solar eclipse, and this one, a full moon near a node, would lead to a lunar eclipse. It doesn't have to be perfect. Okay? So this one, no eclipse. This one, no eclipse. So that means that we need particular conditions for eclipses. Well, then you have to think about how these cycles line up with each other. And it turns out that you have basically a 13-year cycle to get things to line up, which makes eclipses much rarer than just new moons and full moons. All right? So we have about 2 eclipse seasons each year, with a lunar eclipse at new moon and a solar eclipse at full moon. All right? So we do have about two eclipses per year. And then we come back around and have them at the same time of year so many years later. And kind of the process repeats itself. So we can count on 2 eclipses per year. Half the world will always see a lunar eclipse, but it's very rare. You got to be in the path in order to see a solar eclipse. So even though there should be a solar eclipse about once a year, sometimes that solar eclipse only passes over the Pacific Ocean and Antarctica or something, and practically no one sees it. All right? Or it might just not pass over the part of the world you live in. Okay? Maybe, Southeast Asia gets it, but we don't here in North America. Okay? So that's the idea that makes All eclipses, less frequent than phases of the moon, and particularly solar eclipses, very rare because you have to be in its path. All right? So 2 conditions must be met for an eclipse. It must be a full moon for a lunar eclipse. It's a summary. Full moon for a lunar eclipse or a new moon for a solar eclipse. And the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane, called a node. Okay? Eclipses recur with the 18-year, I misspoke and said 13-year, with the 18-year, 11 1/3 day Saros cycle. But type and location may vary. Okay? So the eclipses will occur at the same date, but the type and location can vary because we're not taking into account. So for example, we're always going to get a solar eclipse on the same date, but maybe whereas 18 years earlier it was a total solar eclipse, now it's a partial, it's a ring of fire. It's a annular solar eclipse. It's a ring of fire because the distance of the moon hasn't lined up. Because that's one thing that this whole diagram does not take into account is the elliptical rather than perfect circular nature of the moon's orbit. All right? And then this business with the path being in different places has to also do with the elliptical nature, because that's going to end up having the light cast on different locations on Earth's surface. Okay? And here are some examples. So let's pay attention to some North American ones. So we had one back in 2017. Can't believe it's already been 3 years. This was what was called the Great American Solar Eclipse. It was a big deal. You can see it it looks like it's passing through Washington. It actually passed through northern Oregon. Right? It was on August 21st. I remember the semester had just started. I was teaching at Las Positas College that day. All right. We had a beautiful solar eclipse over here in Northern California. All right. And there's been some since then. But the next one that you should pay attention to, unless you're planning to travel, is in 2024. So in 4 years, on April 8th, there's going to be another one that crosses across a big swath of North America. Okay, and this is the last one that will cross North America in your lifetime. The next one across North America isn't for like another 90 years after 2024. So probably none of us will be alive. So unless you want to travel, this is your best chance to see a solar eclipse. And you still will have to travel to Texas or Tennessee or somewhere, and you can also catch it up near the Great Lakes. Okay? Okay, so continuing on with solar eclipses, we know the path of these solar eclipses as they move across Earth's surface. Okay? The path of totality. Okay, so in summary, half the moon is lit by the sun, half is in shadow, and its appearance to us is determined by its relative position of the sun, moon, and Earth. Okay? Furthermore, we only ever see the features, such as the craters of one half of the moon, because of the synchronous orbit of the moon's rotation or the synchronous movement of the moon's rotation and orbit. Okay? What causes eclipses? Earth shadow for lunar eclipses, moon shadow for solar eclipses. And the tilt of the moon's orbit, the 5-degree tilt of its orbit relative to the ecliptic plane, means that we get at most 2 eclipses per year. Okay? All right, our final section of this chapter, the ancient mystery of the planets. What was once so mysterious about planetary motion, and why did the ancient Greeks reject the real explanation for planetary motion? Okay, so here are the planets that we can see with the naked eye. Okay, so they're the ones that were known in ancient times. Mercury is quite bright but difficult to see because it is so close to the sun. It tends to rise and set with the sun, but sometimes we can see it right after sunset or right before sunrise, and it is quite bright. Okay, but it's often obscured by the twilight light or early sunrise light. Okay, Venus is very bright when visible, but again is only going to be visible for about an hour after sunset or an hour after or before sunrise. Okay, the morning or evening star. It's amazing how bright it can be sometimes. Okay, Mars is noticeably red. Right, it really is the red planet. Jupiter is very bright due to its large size, and Saturn is moderately bright. Saturn and Jupiter recently in the sky have been kind of close to each other near the moon, at least as the moon rises. So like I'd say, an hour after sunset. And you can it always looks like, Jupiter is the big bright one and then Saturn is the noticeably less bright one. All the planets are along a line because they're all in the ecliptic plane. So you can find out, you can guess if it's a planet or a star because you find some really bright dot. You're like, oh, that looks like red and really big. That's probably Mars. And you look kind of along the same arcing line, and you see another big bright dot that might look too bright to be a star, and you're like, oh, that's probably Jupiter. So that you can kind of see the idea of the ecliptic plane, okay, at night. Okay, so moving on. What was so mysterious about planetary motion? Well, planets usually move slightly eastward from night to night. All right. So in a given night, they don't seem to move much at all. But over many nights, over the duration of the full year, they do tend to move eastward, okay? And that's because they're, of course, orbiting the sun like us. But sometimes they go westward relative to the stars for a few weeks. They appear to just start drifting backwards. They're like these weird wandering stars. That's what they were sometimes referred to in ancient texts as wandering stars. Because it'd be one thing if they just always moved one way, but then they drift backwards, right? So here's a good example. Let's start with July. Okay, so here's the 6th of July, 2012. And we're looking at Mars. And so over progressive days, the movement is going to be, so we're going to move, we're going to start here in November 2011. So over progressive days, we're moving steadily in one direction. Let's see if I can find the right way. I think we're moving the right line. Yeah, I think we're going like this. So we're moving steadily in one way. And we're going to get up to this point here, okay? And then it starts to kind of drift this way, but it's moving steadily. So here, I'll actually connect the dots. So it's moving along until we get to January 2012. So we went from November to January, okay? 2011 up to 2012. Then things change. It stops drifting eastward and starts to go backwards all the way up to April, right? So for a couple of months, we have retrograde motion of Mars. And then in April, it finally turns back around and continues on its way east. Okay? And it will continue on its way east for quite some time. It's going to continue for all the way up until November and December of 2012. Okay? So although it did go, for a couple of months, it went backwards. It still spends the other 10 months going in the more normal way of east. But why does it do that? Why would a planet just spend a couple of months drifting backwards, seemingly? Well, because it's all about perspective. It appears to drift backwards if we kind of just assume that Earth is at rest and the planets are just kind of up there doing their things, but Earth is not at rest. Earth is orbiting the sun. So, it's easy for us, perhaps, to explain. It occurs when we lap another planet, or in the case of Mercury and Venus that are inside of the sun relative to us, when they lap us, because the faster planets are the ones closer to the sun. So Earth has a shorter year than Mars. And so every Earth year will come to a point where we pass Mars. Okay? We pass it. And when we pass it, think about passing someone. They appear to drift backwards. Think about passing someone on the freeway. It looks, if you just kind of woke up in a car and looked over and didn't realize you were in motion, it looked like the car that you were passing was just kind of slowly drifting backwards. Until you realize, of course, you're flying forward, so are they, but they're just flying forward at a slightly lower speed than you. Okay? So that's the idea. That's the drift backwards, is just us passing them. Okay? But it was very difficult to explain if you thought Earth was the center of the universe and was fixed, because ancient astronomers thought the Earth was at rest. Okay? So in fact, ancient astronomers did really consider that Earth orbited and we were lapping other planets. That was very much discussed, but they did reject it. Okay? So although ancient astronomers had a pretty good idea about Earth being spherical, based on experiments like a famous one by a Greek philosopher and scientist Eratosthenes, they weren't so sure that the Earth was in motion. Okay? And there's a few reasons for that, but here's a big one. Okay? Why did the ancient Greeks reject the real explanation for planetary motion? It was because they said, okay, if we're in motion, then the stars would have to move. Let's think about it, right? So if we're in motion, then our motion must be really big, right? Because obviously these things are far away from us. That means the Earth is spinning in a huge circle around the sun. And we are, right? 150 million kilometer circle, right? This is a huge circle, a radius of 150 million kilometers. If that's the case, then when the planet's over here and we look up at a nearby star, that star would appear to have certain stars behind it. But then, in January, a half orbit later, when we're 300 million miles away and we look towards that same nearby star, then it's going to have different stars behind it. That idea is called parallax. You can do it right now by standing up, looking at something across the room, you're taking a few side steps, and then looking at how the things behind that something have changed, right? So, look at something sitting across a table, look at the things that are on the wall behind that thing sitting on the table, take some side steps. Are the same things on the wall behind the object sitting on the table? No, of course not, because you've changed your perspective. Okay, we experience parallax all the time, right? Sometimes we compose photographs based on parallax. Like, no, it looks like that tree's growing out of your head. So you take a few steps to the side, and now that the tree's not seemingly growing out of behind someone's head, and you fix the photo, and you take it, right? Push the button. So here's the thing. That doesn't happen with stars. When we look up at stars, we don't see parallax. Now, we can with modern telescopes, but the ancient astronomers really, really could not. They could not observe parallax because it turns out that nearby stars are still so far away that parallax is tiny. Okay? So that was the thing. And that idea, that hypothesis that stars, even the closest stars, were light years away, trillions of kilometers away, was truly inconceivable. All right? It still boggles the mind. And now we know it to be fact. Okay? Stars are so distant from each other that parallax is tiny. It is just arc seconds. Okay? No, arc minutes. Okay? So stars are so far away that stellar parallax is too small to notice with the naked eye. Earth does not orbit the sun. It is the center of the universe. Those are the two ideas. It's either this one or that one. Okay? Well, the Greeks, with a few exceptions, like Aristarchus, rejected one, okay, which of course is correct, and accepted two. But let us reject two and accept one, all right? The stars are so far away that stellar parallax is not noticeable to the naked eye, all right? And the stage was set for a long historical showdown between Earth-centered and sun-centered, all right? And even when the heliocentric model was accepted during the Copernican revolution, stellar parallax was still not measurable. It was still that small. It took more precise measurements to find stellar parallax. And a unit of measurement, which I'll talk about in the next chapter, called the parsec, is actually the measurement of stellar parallax. The smallest measurable stellar parallax is 1 parsec. Okay? And we'll get back to that. All right? So, in summary, what was so mysterious about the planets? The fact that they appeared to drift backwards, apparent retrograde motion. And why did the Greeks reject the real reason? Because they didn't see stellar parallax, and they thought that there's no way stars could be that far away, but it turns out they were wrong. All right. Well, thank you so much for listening to this second video, or watching this second video for Chapter 2, and stay tuned for accompanying videos for Chapter 3.